Good morning, good afternoon, good evening, wherever you might be, and welcome to another one of my science posts. This one is called Weary Light, and I have to warn you at the outset, this one is longer than any other post I've made so far. And I think it is worth it because I think I've untangled a lot of concepts that have become tangled in the popular science imagination. And if you enjoy having your mind stretched and sorted, then this post is for you. I will start this disentanglement process with a simple problem. It appears that there are objects moving apart at faster than the speed of light, and this contradicts the idea that light travels at a maximum speed. So if I try to come up with the simplest possible solution to this problem, I have to divide it into two parts because there are two possible solutions, not just one. In solution A, we see that if space itself expands, then when we see objects moving apart at faster than the speed of light, we can call this an illusion caused by expanding space. We then describe all of physics with a curved Riemannian coordinate system which changes when matter moves. In solution B, we say that if space is defined by a flat Cartesian absolute coordinate system that does not change when matter moves, and if light travels at a maximum possible speed, when it appears that objects exceed this speed, we must conclude that this is an illusion caused by light losing energy as it travels across vast distances. Solution A is consistent with Big Bang standard model cosmology, in which dark matter holds galaxies together and dark energy blows everything apart. Solution B is consistent with tired light cosmology, in which dark matter and dark energy are illusions caused by wakes created by matter that moves relative to an absolute frame of reference. This is the simplest way I can think of to state the problem. But because so many redundant, overlapping languages and definitions have sprung up since the Tower of Babel fell when the nuclear bomb went off, a statement of the problem that draws in all of these terms is as follows. Does light travel to us in straight lines through the expanding, curved Riemannian-Minkowski-de Sitter space of a Big Bang flat universe? Or does it travel to us along meandering rivers in the flat, jiggling space of a gravito-electromagnetism steady-state Cartesian tired light electric plasma round universe? The answer to this question will determine whether galaxies never move faster than the speed of light relative to one another, because once they hit the speed of light, they disappear from the perspective of the other galaxy, and when you can't see something, it doesn't exist. Or galaxies actually move faster than the speed of light relative to one another, and just because we can't see things that are moving away from us at faster than the speed of light doesn't mean that those things don't exist. Your personal preference for one of these options may depend on whether or not your mommy played peekaboo with you when you were a baby, and you absolutely must choose between these languages. Otherwise, you will get very, very confused. I'm trying to organize my workspace, sorry. Either relative to a single point, nothing travels faster than light, or relative to 2 points, velocities can appear to exceed that of light. The choice is between a relative reference frame of the Big Bang and an absolute reference frame of tired light. According to fans of Einstein and the Big Bang, there is no such thing as an absolute reference frame. And if you didn't know better, you might think that Einstein's language is an experimentally proven fact because of Eddington's experiment with starlight and Michelson and Morley's experiment with an interferometer. But it is not. The language is something that Einstein postulated a priori. That is the fancy way of saying that it was an assumption. There are other ways to describe the same system with different a priori assumptions. If instead you ignore Einstein and insist on sticking with your intuition by talking about an absolute reference frame, you have to derive everything in a language that is inconsistent with Einstein's. So, to avoid being a pariah or an outcast, most physicists speak Einstein's language, even though it sounds really weird from a regular person's perspective, because regular people don't look up at the sky with tunnel vision and define curved things to be, Ironically, Einstein's counterintuitive language tends to make regular people think that they aren't smart enough to understand physics, and that seems to be the language's primary function: bedazzlement and mystification of the cosmos. To me, it looks like a stupid marketing trick designed to make people think that physicists are smarter than everyone else. Now, back before I spent 20 years within the physics community, I assumed that, little old me, I don't know anything, and all of these physicists know everything. But if you spend enough time in the community, you realize that the emperor has no clothes. They don't know what they're talking about, unless they're talking about some very narrow, defined system. Once you get into any kind of descriptive application of physics, the sky is the limit as far as nonsense goes. Some believe that the choice between these languages is based on philosophy and aesthetics, but what does experiment tell us? A Big Bang person would tell you that tired light is ruled out because starlight is not diffuse. It is point-like, and it would have been diffuse if the light's energy had been lost through quantum scattering processes, with atoms or molecules spread throughout the cosmos. This is a straw man argument, because there are other mechanisms through which light could lose energy without relying on atomic scattering processes. Michelson-Morley's experiment told us that light does not lose energy when it travels in straight lines. But the Sagnac loop, an experiment done around the same time, it told us that light does lose energy when it travels in circles or curves. Since Eddington's experiment tells us that gravity bends light, it seems quite clear to me that the Sagnac loop experiment implies that light should lose energy as it travels through the cosmos. Yet in the Big Bang framework, this does not happen, because in the strange coordinate system they used, curved paths are defined to be straight, because it is easier to integrate, as in add things up, along a straight path than along a curved one. Tricky, eh? Unnecessarily so? Definitely. I believe that the loss of starlight's energy as it travels along a winding cosmic path can also be connected to the quantum uncertainty principle, in which a minimum momentum change is allowed over certain minimum distances. Each little step corresponds to a little bit of lost energy. And from this perspective, the Big Bang interpretation of astronomical data is incorrect, because it does not fit with what we understand about the uncertainty principle, whereas a tired light interpretation does. I don't understand why astronomers forgot that the weird coordinate system they were using for general relativity was just a static approximation of a dynamic system. The map is not the territory, it's an approximation. And I don't understand why they forgot that Sagnak's and Eddington's experimental results suggest that starlight loses energy and follows curved paths as it travels towards us. The wavelength is not stretching out as space itself expands in a Big Bang universe. Then again, scientists often underestimate the role that religion plays in their preference for a theory. Just ask Galileo if religion influences theory preference. Who could resist a poetic Big Bang narrative with a dramatic let there be light moment? Tired light from stars that may have been burning forever sounds so tired in comparison. Maybe tired light just needed some more clever marketing. This issue is quite muddled in popular discourse because the examples taught in school or in popular science media usually knock tired light down like a straw man while leaving Big Bang LCDM cosmology standing tall as a sort of monolithic entity, big science. The story told is that steady state or tired light theory posits that the number of photons per second from each object drops in proportion to the square of the distance, while the number of objects increases with the square of the distance. And since this isn't what we see, tired light theory must be wrong. This is a straw man argument because, unlike Big Bang theory, the beginning of time is outside of tired light's purview, and in any case, just because you can't see a certain star doesn't mean that it doesn't exist. I can imagine a scenario in which a star is invisible because it is vibrating in a mode that is out of sync with our own. A grade school teacher would explain the concept in terms of a child being pushed on a swing. If you are pushing at exactly the wrong time during every swing, there will be no energy transfer. And if your eyes were closed, you wouldn't even know that a person was swinging. You wouldn't even see the star. When there is no energy transfer, you are blind to each other, and it is possible for us to be blind to distant stars in this way. A physicist who thinks in the spatial domain would explain that if the atoms in the distant star are moving back and forth at faster than the speed of light relative to us, they will be invisible to us. A physicist who thinks in the time domain would explain that if the atoms in the distant star are emitting light that is out of sync with the light we emit, light will interfere destructively and we will be invisible to one another. These explanations are geometrically equivalent, and they are consistent with the worldview of people from the past, like Maxwell, Jurkinus, and Hertz, pre-World War II physicists. They looked up at the sky and saw stars in jiggling jello. It isn't a bad heuristic, it just went out of fashion. Those sorts of physicists wouldn't have been mystified by observations like the eclipticity of the cosmic microwave background. But modern physicists, without this heuristic, are in a constant state of befuddlement about basic things. So far, I've conflated steady state and tired light theories while contrasting them with the Big Bang theory. Since physics must be rigorous, it is time that I define these terms more precisely. The Big Bang universe expands at an accelerated rate while the speed of light is constant. The tired light universe expands at a constant rate while light's speed decreases with distance between the source and the observer, while the steady state universe is static, while light's speed decreases with increasing distance from us. Now I will break each of these things down into a question of how do we know that any of these models are correct? So starting with the first one, how do we know that the universe is expanding at an accelerated rate while the speed of light is constant? These are the assumptions behind the Big Bang paradigm, in which gravity is explained by the accelerated expansion of space itself. This heuristic involves masses sinking into space that grows progressively more spread out over time, and it is supported by prominent pop scientists. The position of this paradigm, this LCDM cosmology paradigm in the firmament, was reinforced by the 2011 Nobel Prize given to American physicists Rice, Perlmutter, and Schmidt, a prize which has since been called into question by a reanalysis of the data in 2016. It appears that the Nobel Prize winners failed to take the motion of the Earth into account when they estimated that the universe was accelerating. They confused the acceleration of the Earth with the acceleration of the universe. Oops. I drew attention to this back in 2017 when I discovered Sarkar's work from 2016, and pop scientist Sabine Hossenfelder has recently made a video about the importance of Sarkar's work. She's now starting to question fundamentals as well. Basically, it seems like Rice, Perlmutter, and Schmidt confuse the motion of the Earth with the motion of more distant stars. And when you look at more of the stars, this error becomes obvious. What isn't clear is why the community doubled down on this mistake by granting the 2019 Nobel Prize to James Peebles, a man who built his career around Big Bang cosmology. Okay, so that is the idea that we think we know that the universe is expanding at an accelerated rate while the speed of light is constant. And I think we have experimental evidence that this is a trade-off between deciding that the Earth is in motion or that the entire universe is in motion. And I think most people would conclude that the Earth is in motion because that just makes more sense. It doesn't require you to tie your brain in knots so much. So based on making sense and not tying your brain in knots, I think we can reject the Big Bang cosmology. And that leaves us with the next option. How do we know that the universe expands at a constant rate while light's speed decreases with distance between the source and the observer? These are the assumptions behind the tired light paradigm. And the gist of the idea is that the expansion of flat space is described by gravito-electromagnetism, Heaviside's 1879 theory of absolute space and time, that somehow got replaced by Minkowski's curved space general relativity in 1921, when World War politics, coupled with Eddington's experiment with starlight during a solar eclipse, turned Albert Einstein into the poster boy for physics. So, to try to think about this shift in the most simple terms possible, Imagine stars as a bunch of boats traveling away from one another, and that the wakes behind those boats is what drives them apart. So, and then what you have in general relativity is an approximation in which space is curved, in which the turbulence of those behind those boats is instead represented by curved space. Yeah, I'll get into that a little later, hopefully with more clarity. People got all excited about the idea of bent space without understanding that just because a few effects can be described or calculated more easily with a bent coordinate system, that doesn't mean that the coordinate system depicts reality. This is analogous to the confusion of people who believe in a flat Earth, who look at a picture of a round Earth and say that it only looks round because of an optical illusion. Most events are better represented by flat coordinate systems, and it makes more sense to say that space is flat and bending or slowing of light is caused by how mass or charge alter the properties of space through turbulence that slows the propagation of light. In this way, the cosmos can be described with the same language that we use to describe optical systems. Mystery solved. No need for more funding. Go do something more useful. I am fond of the tired light paradigm because it is so easy to marry it to quantum mechanics with localized vibrations of space that make things heavy in the same way that causing a pan of sand to vibrate will make the objects in the sand act heavier. Similarly, mysterious dark energy and dark matter don't exist in this universe because dark energy is just the positive deviation from what general relativity predicts for masses that are not moving, and dark matter is the negative deviation from what general relativity predicts for masses that are not moving. When you know that masses are moving relative to one another, or when you assume that, general relativity will obviously deliver erroneous predictions of matter that doesn't actually exist. And in this tired light universe, there is an openness about this fact, whereas in the Big Bang universe, that fact is sort of pushed under the rug, and students are told to go off and look for dark matter, particles of dark matter, something that doesn't objectively exist. So to be more specific, dark energy is the apparent result, the illusion caused by masses moving in the same direction relative to each other, as in boats, the wakes of boats pushing the boats apart. And in some case, you might just have a boat that's just sitting in one location and vibrating, and that causes a wake around it. And so maybe boats isn't the right analogy. You should picture a shaking object in water causing ripples around it that push everything around it apart. Meanwhile, dark matter is the apparent result when masses are moving in opposite directions relative to each other, as in the spiral arms of a galaxy. So I said at the beginning of this section that I had conflated tired light cosmology with steady state cosmology. And here I will show what happens if you take one step further. Whereas in this tired light universe with gravito-electromagnetism, we still talk about the distance between things increasing at a steady rate. So in the Big Bang universe, the distance between things is accelerating apart. And in the tired light universe, the distance between things is moving apart at a steady rate. And then in the steady state universe, the distance between things is not changing at all. There's all of the apparent movements of things apart are explained as illusions. So how might we know if the universe is static while light's speed decreases with increasing distance from us? These are the assumptions behind the steady state paradigm, which was favored by Fred Hoyle before he quit physics in disgust with his colleagues. Whereas the tired light paradigm is consistent with how we describe an optical system, the steady state paradigm is consistent with how we describe solid state systems in equilibrium, like a room temperature superconductor. This is sort of like tired light, but with more optimistic assumptions about entropy than Newton's second law suggests. The idea is that entropy is positive on some length scales and negative on other, more lively length scales. In accordance with Newton's first law, energy is transferred back and forth between the two states without ever being created or destroyed. I find this also a very appealing system. So I think, though, if you use this one, you can't use... So the Big Bang theory has to use Lorentzian transformations with Lorentzian Maxwell's equations. And then tired light, as I've defined it, requires Galilean transformations with Galilean Maxwell's equations, which are comparable to Heaviside's gravito-electromagnetism. And in the steady state universe, you have to do something even... It's Galilean Maxwell's equations, which are not the same as Heaviside's approximations of gravito-electromagnetism. So I think it basically boils down to each of the different universes uses more or less approximations in the definition of Maxwell's equations. And if you're confused by my use of the concept that there's more than one version of Maxwell's equations, I wrote a post on that. It's not something that I learned at the undergraduate level more than in passing, but once you start thinking about things in terms of the different approximations made within different types of Maxwell's equations and how those approximations produce different cosmologies, the whole world of physics just sort of falls into nice, clean categories, and it helps you see how the different subspecialties are working within different frameworks, often without knowing it. So it's overly complicated. So this leads into a question of how do we know that it's possible that all of those different frameworks are valid ways of describing the system? Why can't they all be true? And with physics, you can always describe a system in multiple languages and not be wrong about any of them. You tend to choose your favorite language based on how precisely it quantitatively describes a given effect, and some languages may be better qualitatively and others are better quantitatively. But if you aren't aware of which language you are using and how to translate from one language into the other, you're lost. And that seems like what a lot of astronomy is today, just completely lost and confused. That was at least my conclusion when I started to understand how astronomers apply relativity to their data, and I saw that it was different than how accelerator physicists apply relativity to their experimental data. So it's also possible that none of these three methods, these frameworks, are valid ways of describing the system, because all of the languages of physics are and will always be approximations of a system about which we will never be able to know the initial conditions and will therefore never be able to fully predict. That's what quantum mechanics tells us, that when you don't know the initial conditions, you end up with strange correlations that don't make that much sense, like entanglement and such. But that's just because you don't know the initial conditions, even if you have a deterministic system. If you try to simplify this into a single statement, it all boils down to, is a star moving away from us, or does it just look like it's moving away from us? How can you tell? Since astronomy is a descriptive science and not an experimental one, we can't decide this based on which theory has superior predictive power. Instead, one might make this choice based on the degree of self-consistency an individual theory possesses. And if that were the measure, then the Big Bang theory would probably win because it's been so heavily developed. But I don't think that's a good idea, because the Big Bang theory does not fit very well with other branches of physics. And I believe that the choice of theory should be based on how well the theory fits with all other theories in existence, so that you end up with a more holistic meta measure of self-consistency, a more universal language that is easier to teach people and that doesn't contradict itself, because people are not aware that there are three different versions of Maxwell's equations, and you never know which version the person you're talking to is using. People who've been conditioned to imagine a Big Bang bubble that expanded at greater than the speed of light and then popped often find it difficult to imagine anything else. Those who believe in the Big Bang say that there was an inflationary epoch during which particles traveled faster than light, just like the standard model virtual particles within collider experiments that temporarily violate conservation of energy. Then, all of a sudden, for no discernible reason, we are supposed to believe that the laws of physics suddenly changed, and everything that happened since must travel at less than the speed of light. It's kind of a wild story. It's the transition from, I saw André Linde, a prominent physicist. He told this story in a Slack conference room when I was just a child, more or less. I've since been amazed by how much sandcastle empire building resulted from this lark. Some of those who founded the theory have since abandoned it, while the man who stood beside it won the 2019 Nobel Prize. That's James Peebles. The message that students should get from this is that loyalty to the group pays off. Perhaps Big Bang believers are being such sticks in the mud because they want to protect their friends in particle physics. All it takes for a tired light theory to match experimental evidence is for the energy of light to be lost in unmeasurably tiny steps when it interacts with gravity over long distances. And all it takes for that to be true is for light to have a tiny bit of mass. But most physicists wouldn't like this because it would pull the rug out from underneath their reverse-engineered standard model particle zoo, and out from underneath all of neutrino science. The discrepancy between Big Bang and tired light universes gives you an estimate of light's mass, but people don't try very hard to figure these things out when astronomers frame tired light as a straw man and insist on misapplying relativity by applying it to macroscopic objects rather than just to fundamental particles. It's a major error. So as an outsider, I ask stupid questions like, does the math work out in a tired light universe if we just start calling neutrinos light, or saying that light is the same thing as a neutrino, and we've been confused about it all along? I genuinely don't know, but the amount of nonsense I've seen in physics has caused me to take even crazy-sounding questions seriously. Meanwhile, the questions that are taken seriously within cosmology involve an incomprehensible incompatibility of Big Bang general relativity with quantum mechanics, and this mystery has been used to ask politicians for more money for the past 60 years. And I put the word incomprehensible in italics because it is... Oh shoot, I just killed my window. No! Now I don't have my text anymore. Will it come back? Okay. I have no text. All right, so that it's not incomprehensible why the Big Bang universe and quantum mechanics are incompatible, because they're using different coordinate systems. Quantum mechanics is in a flat coordinate system, and the Big Bang universe is in a curved coordinate system. When you try to mix apples and oranges, you shouldn't be surprised that they don't match. Okay, I got my text back. What I notice in typical pop science writing that is unaware of how physicists mix apples and oranges is how tired light, steady state, gravito-electromagnetism, and plasma cosmology and electric universes are each individually knocked down as straw men, and that this is a divide and conquer technique because all of those theories could be very much the same when combined in one unified framework. It is only when they are separated and given their weakest interpretations that they fall down in comparison to the state-subsidized Big Bang theory. What is really bothersome about this style of thinking and marketing is that the issue is painted in either-or terms, when a recursive, self-similar fractal definition of the system may be more appropriate. We clearly have flat space over some length scales and curved space over others, just as the Earth is flat when you are standing on it and curved when you are high above it. I suspect that the universe works the same way, and when we approximate curved things as flat and flat things as curved, there is something deeper going on regarding a self-similar fractal structure in which light acts more and less tired depending on how curved or turbulent the space is. Recall that curve and turbulence are two ways to say the same thing in the post-Tower of Babel world of physics today. I'm sure I've confused you very much, but climbing out of the self-contradictions of modern physics is hard for everyone. And you may have to write something like what I'm doing, do something like what I'm doing right now in order to untangle it yourself. It may seem that silly questions of language and theory don't matter, but how people view the cosmos has profound psychological impacts. If you think that you live in a Big Bang universe that's destined to die a long, slow, cold heat death, that makes you feel small and insignificant and powerless. But if you believe in a steady state universe where everything is kept alive by this vibration which causes negative and positive entropy, where order appears on one scale when it disappears on another length scale, that is somehow more lively, and you're part of everything. It's a universe in which you're connected to something greater, and that's more inspiring. So I think these are a paradigm shift in physics could be really a good thing for people to feel more connected and better about their place in the world. It's a quasi-religious issue. In a Big Bang universe, it's kind of, a god is something distant. It's disconnected from you. It happened, its arms may be long, but they, but in a steady state universe, it's kind of like a godlike force is powering everything, and it's connected to everything. Is your God far, far away, or is your God with you all the time? I think, yeah, you can think of it like that. When a community congeals around one narrow viewpoint, it buries experimental work that will broaden people's perspective. So it's not just a philosophical issue, it also has real impacts on the types of research that is allowed to take place. One example of a person's work which was buried by the Big Bang monolithic community is that of Halt and Arp. Halt and Arp studied quasars and noticed that they often seemed to be in the vicinity of strangely shaped galaxies. He suggested that quasars' extremely large redshifts might be interpreted in two very different ways. Quasars are extremely far away baby galaxies, and their redshift is caused by the accelerating expansion of the universe, as in a Big Bang universe. Or quasars are not so far away, and their redshift might be caused by their ejection from the center of a nearby galaxy. How might one decide between these two options? Well, you would take data, of course. But what happens when the only people who are given money to take data are the people who believe that quasars are baby galaxies? Something very non-scientific happens. The people who want to study the idea that quasars have been ejected by nearby galaxies, they get marginalized and excluded from conferences. They are not given access to telescopes or students. Ignoring the politics, I look for counterexamples to disprove a theory. In the case of the baby galaxy quasar theory, one might look no further than quasar 3C 279, observed in 1971. This quasar appeared to be ejecting something that was moving away from the quasar core at 10 times the speed of light. And over the following years, several more examples of quasars with this strange feature were found. How did Big Bang cosmologists explain away this physically impossible result? Well, they could have used a different theoretical framework, but instead they invented another unlikely result to counteract it. If the jet just happens to be shooting towards us at the speed of light, for whatever reason, this would explain the apparent faster-than-light motion of the transverse components. But I think this seems like a pretty weak leg on which to balance all of Big Bang cosmology. And how do you estimate the statistics of how many galaxies should be shooting towards us at the speed of light? That's not an easy problem. What happened here with poor Halt and Arp? Were idiots directing the research dollars, or were they directing the research dollars based on goals that had absolutely nothing to do with figuring out what is true? My guess is that the latter was the case. The people controlling the purse strings would choose research programs that would strengthen their control over a larger portion of the research pie. When Big Bang cosmologists and quarky collider physicists teamed up to join their narrative and create a mysterious dissonance between their two worlds, well, they ate the whole research pie. Changing a majority opinion is difficult when true believers say that the Big Bang Theory should be chosen based on the depth of the body of work that is already being produced. I don't think that is logically sound. You can have a deep yet wrong theory and a shallow yet right theory. As in the case of Halt and Arp's work on quasars, the depth just hasn't been achieved because efforts have been invested elsewhere. So I will wrap this lecture up with a series of questions posed by a Big Bang physicist to a tired light physicist. They often can't even fathom that there is an alternative, and so they see that their theory explains all of these questions, and they want to know, does this other theory also explain these issues? So what is the theoretical basis for tired light? The idea is that there is a fluid-like ether, a matter ether, not a luminiferous ether. There's a distinction, and you should understand it, which slowly takes energy away from a light wave that is propagating through it along curved trajectories. This makes the light coming from more distant galaxies appear to have a longer wavelength, redshift. In order to match the point-like appearance of light in the night sky, this energy loss must be non-discrete on the atomic scale, as in it does not correspond to quantum scattering processes off of large particles. Maybe it involves smaller particles that are harder to measure, the scattering processes, or impossible. Or maybe if there is such a thing as a graviton, the scattering might be discrete on the scale of planetary bodies. But these unmeasurable issues don't invalidate the theory. Just because you can't measure certain aspects doesn't make the theory invalid. And I think that earlier, we've established that the Big Bang Theory has gotten the accelerating expansion of the universe wrong, and it seems to have gotten quasars wrong too. So when that happens, you look for an alternative that has more self-consistency heuristically, and I think that tired light and steady-state universes offer that self-consistency, and they also offer consistency with other subdisciplines within physics, like, for example, optics or superconducting materials science. So another question is, why do high-redshift galaxies have a different chemical composition compared to low-redshift galaxies? Why do they look less mature? Big Bang physics explains why this is the case. I think a tired light physicist would say that the light from the stars took a long time to get to us, so what we see was generated a long time ago. And if all of the stars started to burn at around the same time, That is why the night sky is not uniformly filled with light. This is just the age-old Olber's paradox explanation, and it fits with either a Big Bang or tired light universe. But if you want to describe a steady-state universe instead, in terms of the ages of galaxies, you need a model of the universe as a fractal circuit in which light is continuously exchanged between stars. It is a bit harder to wrap your mind around that picture, but it is possible, and I think that this is the direction we will eventually go in. It's just harder for people to understand those systems, perhaps today. Maybe we'll be smarter in the future, and more people will understand those systems, a steady state picture. But at the moment, we're at kind of a rudimentary Big Bang understanding, which I think will evolve into a tired light understanding, and then eventually we'll get to a steady state understanding. But perhaps people understood this in the past better than we do. If you look at a Himalayan singing bowl and how you can create bubbles in that bowl, some people today might understand that this is representative of the physics of our universe. It's like a little universe in a bowl. But physics today, modern physics, does not have this level of holistic, unified understanding or a language that maintains self-consistency and coherence. It's degenerated. Okay, another question. I'm almost done here. Why does the large-scale distribution of matter obey certain statistical laws? The Big Bang theory explains how this works. What does tired light say? I think a tired light physicist would explain that fractal structures obey certain statistical laws, and our universe is certainly self-similar over many key length scales. On this point, the main difference between a Big Bang perspective and a tired light perspective is in how they each define space. The Big Bang person says that the space between things changes depending on relative motion. Think of the wake behind an accelerating object giving the illusion of that the two objects are closer together, because if there's a wake behind an object, the objects are going to act like they're closer together because the wake pulls them in, I guess. Yeah. Whereas the tired light theorist would say that the space between two objects, the distance, is a constant when they're moving along. It doesn't change depending on their motion. It only seems like it changes because of their motion. So they act like they're closer or further apart. My phone. For example, if you and someone behind you are both accelerating through some substance, the more you accelerate, the more the space between you will act like it is larger, even if the distance between you didn't actually change. How you interpret the situation is just a matter of convention. Some conventions are easier to understand than others, and I would argue that the least counterintuitive description should win the game. As in, when you explain it to your grandma, she shouldn't think that you are nuts, as is often the case with the exploding bubble, Big Bang, Lorentz contraction story. I think we would do better with a tired light, Galilean system. And you can write Maxwell's equations with Galilean transformations. Concerning the Big Bang, my inner grandma still asks, just like we started off with at the very beginning of this whole story. How can two galaxies be moving further apart at faster than the speed of light if nothing can travel at faster than the speed of light? My inner physicist answers, blah, 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 de Sitter space, but this never fully satisfies my inner grandma. I have to remind her that it is impossible to think in Riemannian-Minkowski de Sitter space because our minds work in Cartesian ways. This is just, this form of this strange coordinate system is just a trick used to make certain calculations easier. But many physicists forgot that and started confusing the map and the territory. So another question is, why is there a cosmic microwave background? Big Bang theory tells us why. It's the leftover heat from the initial explosion. But a tired light physicist would say, this microwave background is just caused by the fact that empty space is warmed up by the light of the stars. And if space were truly empty, then the light wouldn't lose energy as it traveled through it. Big Bang theorists' mystification of this radiation, the fact that empty space isn't truly empty, it resulted from the assumption that space is empty. That's kind of silly, or? So another question is, why is the angular power spectrum of the cosmic microwave background radiation what it is? I think a tired light physicist would explain that when energy flows through an inhomogeneous medium, as in rivers of light produced by stars, it concentrates in bottlenecks and is relatively homogeneous at a distance from the bottlenecks. The peaks in the spectrum correspond to various length scales or correlation lengths over which there is homogeneity and connectivity. Where energy concentrates, you get negative entropy, as in increasing order, life, and time travels forwards. In a Riemannian-Minkowski de Sitter general relativity metric, the light travels straight ahead, but the space curves. In a Cartesian metric, the light travels along curved rivers, but the space is flat. And in order to understand the power spectrum, you need to do renormalization in a Cartesian coordinate system. If you do renormalization in a curved coordinate system, you won't get the result that is consistent with tired light cosmology, of course. Another question, I think this is the last one. Yes. Why do primordial hydrogen, deuterium, and helium have the observed ratios? Big Bang physics explains this. I think a tired light physicist would look back at history and say that Fred Hoyle, the man who invented nucleosynthesis, he, of course, believed in a steady state sort of universe, and he didn't believe in a Big Bang. Yet, the Big Bang people labeled him as a fringe thinker at the same time that they adapted his nucleosynthesis theory to their own framework. So they took his idea and then called him a fringe thinker. I think that tired light and steady-state universes are only debunked or fringe in the minds of people who set them up as straw men in order to support the image of the big physics industry as powerful, single-minded, and all-knowing, when upon closer inspection, it's anything but. I mean, when you go into it, you think, these people know things, and then, yeah. So I think it's instructive to compare this narrative to the most recent announcement of the 2019 Nobel Prize in Physics. And if you click on the blog post and the link, you'll see a video of that and also a video of James Peebles delivering a lecture on the Big Bang universe, so he pretty much represents that theory. This is for a contrast to my attempt to figure this out. I first posted this material on Quora, and I'm compiling my science writing into a 2-book set. But instead of editing that work, I am procrastinating by blogging and making these videos. I might be able to publish the book in a few months if I really get to it. Until then, the only long-form work I have published is in the form of fiction that is safe for kids, but while being interesting for adults. And I think it's a lot more fun to read than this kind of stuff. So I recommend it to you. I am trying to learn to write in an accessible manner about topics that are widely believed to be too complicated to understand. Any feedback you can offer is welcome. I probably bit off more than I could chew in this talk, but I hope that somebody got something out of it, even if it was only me. Until next time, thank you for watching.